Hello everyone, and welcome back to our series on algorithms. In the last video, we introduced minimum spanning trees and how they can be computed using Kruskal's and Prim's algorithms. In this video, we will discuss the two main algorithms used for traversing graphs, BFS and DFS, and how they can be used for various different purposes. If you enjoyed this lecture, be sure to like, comment, and subscribe. With that, let's begin. Before we discuss BFS and DFS, we first need to clarify some details about graphs. Specifically, in the previous video, we neglected to mention how graphs can be encoded, since it wasn't particularly relevant to the algorithms we were describing. However, for this video, how we choose to represent our graph becomes important when we analyze the complexity of these graph traversal methods. In particular, rather than naively storing sets of vertices and edges, we can use more efficient structures. One such structure is an adjacency matrix, where for a weighted graph G equals VEW, each element Aij is equal to Wij if Ij is in E. If Ij is not in E, then Aij is set to either 0 or infinity, depending on whichever is appropriate for the given context. Note that if we have an unweighted graph, we can simply assume that Aij equals 1 for all Ij in E. The other important representation is the adjacency list, which is essentially a map between vertices and lists of their neighbors. If the vertices are labeled via an enumeration, you can think of this structure as a list of lists. With this, we are now ready to discuss the two main methods of traversing graphs. Breadth first search, or BFS, is a method in which we traverse a graph one level of depth at a time. What this means is that if we start from a given root vertex, we will first visit the root, then all vertices which are one edge away from the root, followed by all vertices which are two edges away from the root, and so on and so forth, all while avoiding revisiting vertices that have already been traversed. The algorithm halts once there are no more vertices left to visit. If you map out the paths traveled by the algorithm, the end result is a tree which connects the root vertex to all the vertices it is connected to, meaning that if the graph is connected, this tree will span the entire graph. Moreover, for an unweighted graph, this tree will actually contain all the shortest possible paths from the root vertex to any other vertex in the tree. This is a solution to what's known as a single source shortest path problem for the case where all the weights of the edges are the same, and they are all non-negative. We will discuss in great detail how to solve these problems for non-trivial weight functions in the next video, where we talk about Dijkstra's algorithm. Now that we have intuitively described how BFS works, let's formalize an algorithm for this process. Suppose we want to perform BFS from vertex U. Mark vertex U as being visited and all other vertices as being unvisited. In this case, when I talk about marking vertices, you can interpret this as meaning that we keep track of a map which returns true if a given vertex is visited and false otherwise. Initialize a first in first out Q, and add U to the queue. While the queue is not empty, pop from the front of the queue and call the resulting vertex V. For all of V's neighbors W, if W has not been visited, add it to the queue, mark the vertex as visited, and set parent of W to be V. This is the most basic skeleton for traversing a graph using BFS. If we want to do any additional steps, we can simply modify the algorithm accordingly. For instance, if we want to figure out the minimum distance from each vertex to a given root for an unweighted graph, we could also update a distance map at each iteration whenever we add a vertex to the queue. In particular, we would have that distance of W is simply set to be distance of V plus 1. To calculate the worst case time complexity of BFS, we can make a few observations. Namely, since we have to look at the neighbors of each vertex and check if the vertices are visited and or add them to the queue, both of which are constant time operations, we have that the task of iterating over all neighbors for all vertices is O of m, in the case of an adjacency list. Furthermore, since we also have to iterate over all vertices themselves, we have that the total time complexity is O of n plus m if our graph is defined in terms of an adjacency list. On the other hand, for an adjacency matrix, this complexity turns out to be O of n squared. The second method of traversing graphs is known as depth-first search, or DFS. With this technique, rather than recursively traversing nodes in the graph one depth at a time, we simply travel as far as we can along a given path in the graph before we meet a dead end, at which point we backtrack until we can find another unvisited vertex to travel to. Like BFS, DFS also creates a tree. However, this tree is not a solution to the single source shortest paths problem. The basic algorithm for DFS is quite similar to that of BFS, with the primary difference being that we use a stack rather than a first in first out queue. First, we initialize a visited array as well as a stack S. Add the starting vertex U to the stack. While S is non-empty, pop vertex V from the stack. If V is not visited, mark it as visited, add all of its neighbors W to the stack, and set parent of W to be V for all W. The time complexity for this algorithm is again O of n plus m if we represent our graph in terms of an adjacency list. This is simple to see, as in the worst case, we check every edge of the graph twice and we have to travel to each vertex, meaning that if we represent the graph as an adjacency list, the complexity is O of m plus O of n, which is O of n plus m. On the other hand, if we instead use an adjacency matrix, this time complexity becomes O of n squared. DFS has several different applications. For one, it can tell us about how a graph is connected internally. Since DFS visits all vertices reachable from a given vertex, we can iteratively run DFS on vertices that have not been visited to identify the disjoint connected subgraphs which compose the actual graph. These disjoint connected subgraphs are known as undirected connected components, or UCCs. To find UCCs, we simply add an external loop which iterates over all vertices, where if a vertex has not been visited, it will run DFS from that node. Each time we run DFS, we will assign the vertices to a new component, thereby allowing us to construct the UCC decomposition. Another application of DFS is assigning an ordering to the vertices of a graph based on the order in which they are traversed. A pre-ordering refers to an ordering of vertices based on the order in which each vertex is first reached via DFS. A post-ordering refers to an ordering based on the order in which each vertex is last visited via DFS, which includes backtracking. And we can also define reverse pre-orderings and reverse post-orderings, which are simply the pre-ordering and post-ordering in reverse, respectively. Up until this point, all graphs that we have been talking about have been undirected, meaning that it's possible to traverse both ways along a given edge. A directed graph, however, has directed edges, meaning that we can only travel along the directions specified. Note that for a simple directed graph, which is what we will be dealing with, just like we did for the undirected case, we allow at most one edge with a given source and destination vertex, meaning that we can have up to two edges between any two vertices, which would therefore go in opposite directions, thereby allowing us to have bidirectional edges. Both DFS and BFS can be applied to directed graphs. However, we will focus on the applications of DFS in this case. In particular, let's look at a variant of the DFS algorithm known as DFS with visit times. The idea behind DFS with visit times is that we want to keep track of the pre-visit and post-visit times for each vertex. You can think of the pre-visit time as referring to the first time in which we reach a given vertex using DFS traversal, while the post-visit time refers to the last time we visit a node when backtracking. Each step of traversal, whether that be traveling to a new node or backtracking, is considered a single time step. To compute visit times with DFS, it's somewhat easier to discuss an alternative recursive formulation for DFS. In this case, the stack is implicitly built into the algorithm via recursive calls. As you can see, we have a pre-visit and post-visit routine defined in this version of the DFS algorithm. To compute visit times, we simply have pre-visit be setting pre of v to be clock and incrementing clock by 1. We also do the same with post-visit, but we modify post-v instead. We can then define a function interval of v, which returns an interval from pre of v to post of v. Using these intervals, we can actually classify edges into three main categories: forward edges, backward edges, and cross edges. A forward edge is an edge which points from a vertex in the tree to one of its descendants. You might also see this be distinguished from the notion of a tree edge, which is an edge that is directly included in the DFS tree itself. In either case, we have that interval of v is a subset of interval of u. A backward edge is an edge that goes from one vertex to one of its ancestors in the tree, meaning that interval of u is a subset of interval of v. A cross edge does neither and implies that post v is less than pre of u. Here's an example of a graph with all three types of edges, in addition to the aforementioned tree edges, corresponding to the DFS tree used to compute visit times. Let's look at one application of using DFS with visit times. A strongly connected component, or SCC, refers to a directed subgraph where there exists a directed path between every pair of vertices. Using DFS with visit times, we can compute the SCC decomposition for a given directed graph. Before we explain this algorithm, let's make some observations and discuss some relevant terminology. A graph is a directed acyclic graph, or DAG, if and only if it has no back edges. We define a topological sorting for a DAG as some enumeration pi such that for every edge u, v in the graph, pi u is less than pi of v. Note that since all edges except back edges have post v less than post u, we have that sorting vertices of a DAG in reverse post order gives us a topological ordering. We now observe that if we take a graph with several SCCs, we can condense each SCC into a single vertex, and we are left with a DAG. We can even produce a topological sorting of SCCs by using the maximum post value across all the vertices in each SCC. You can prove this rigorously by considering two SCCs connected by a directed edge, and then looking at the post time of the vertex that is visited last in the union of the two SCCs. Let's now consider how to calculate the SCCs themselves. Note that if we perform DFS, we are guaranteed to explore the whole SCC that contains the starting vertex. However, if this is not a terminal SCC, we could also end up exploring other SCCs as well. To get around this, we explore the SCCs in reverse topological order, meaning that we perform DFS and SCCs with the earliest max post times so as to only explore only one SCC during each run-through of DFS. We can compute reverse topological order for a given graph G by simply computing DFS on the reversed graph G dagger, which is essentially a copy of G where the directions of all the edges are flipped. Putting all these observations together, we have the following algorithm. Create the reversed graph G dagger of G. Run DFS with visit times on G dagger until all vertices have been visited. Run DFS on the vertices of G in order of decreasing post dag times, skipping vertices that have already been visited. Label every subset of vertices that is reached from a given starting point as a separate SCC. Since creating GDAG takes time O of n plus m, and the two DFS run-throughs take O of n plus m for an adjacency list, the overall worst case runtime is O of n plus n. This algorithm is known as Kosaraju's algorithm. Note that you may see this algorithm be phrased in alternative fashion, with DFS being run on the original graph G to compute visit times, and the second DFS being run on the reversed graph G dagger. But regardless of which formulation you prefer, they accomplish the same thing. This whole section of the video on SCCs was conceptually quite heavy, so if you have any further questions about any of these steps, feel free to go back and rewatch it, or leave any questions you have in the comments below. Overall, BFS and DFS have countless applications that we didn't get to go into in this video, such as solving mazes and efficiently detecting cycles in graphs. I recommend you look into these applications further if you found this video interesting. In the next video, we will explore how to solve the single source shortest paths problem for general weight functions using Dijkstra's algorithm and Bellman-Ford. I hope you enjoyed this video, and I will see you next time.